Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
It's a real pleasure to be here.
This is Andrew and Renee. Welcome to the Stack series.
Today, we are turning our attention to the fundamental nature of reality itself.
Today, we are exploring the black hole information paradox.
You know, it sounds like such a niche problem in physics, doesn't it?
Right, something super theoretical tucked away in an academic journal.
Exactly, something for people with too much chalk on their hands to worry about in a basement somewhere. But this isn't just some abstract physics problem.
No.
It's a war. It's a 50-year intellectual war that it's really torn the physics community apart.
I really like that framing, a war.
Yeah.
Because we usually think of science as this collaborative effort, building on each other's work.
Right.
But you're describing a battlefield. And the combatants aren't just the scientists, are they? The combatants are the laws of physics themselves.
Precisely. It is a direct, head-on confrontation between the two pillars of 20th century physics.
Okay, lead them out for us.
So on one side, you've got general relativity. That's Einstein's beautiful geometric theory of gravity, of curved space-time, the macro world. It tells us how planets orbit, how galaxies form.
The big stuff.
The big stuff. And on the other side, you have quantum mechanics, the rule book for particles, for information, for the micro world. It's how atoms bond, how your phone works, how lasers work.
So for decades, they just stayed in their own corners of the ring.
They did. They pretty much ignored each other. But inside a black hole, they are forced into a cage match. There's no escape. They have to confront one another.
And what are the stakes here? Because when I hear paradox, I think of, those fun logic puzzles or time travel what-ifs. This feels bigger.
Oh, much, much bigger. This is about the very stability of space-time. It's about whether the universe is deterministic.
Meaning, can we predict the future if we know everything about the present?
Exactly. Or can information be truly irrevocably erased from existence? Think about it. If the paradox goes one way, our understanding of quantum mechanics breaks. Everything we know about, chemistry, particles, it's all on shaky ground.
And if it goes the other way?
If it goes the other way, then Einstein was wrong about something fundamental with gravity, and space itself might not be the smooth, continuous thing we think it is.
So no pressure then, just the fabric of reality hanging in the balance.
That's pretty much it. And the journey we're going on today is just fascinating. We're going to trace the whole arc. We'll start with Stephen Hawking's 1974 bombshell that basically started this whole mess.
Right.
Then we'll get into the firewall crisis of 2012, which suggested space might just end abruptly. And finally, we'll talk about the really recent breakthroughs from 2019 involving things called islands and wormholes that might, and it's a big might, be solving the whole puzzle.
Okay, let's do it. Before we get to the crisis, though, we need to set the scene. This is our first section, foundations. What did we think we knew before Hawking came along and just threw a giant wrench in the works?
We have to start with the classical picture, the view purely from general relativity. And in this picture, a black hole is, it's shockingly simple.
Simple is not the word I would have chosen.
I know, but it is. There's this concept called the no-hair theorem.
I've always loved that name. It was John Wheeler, right?
Yeah.
The idea that black holes are bald.
In a manner of speaking, yes.
Yeah.
The theorem states that a stable black hole, once it settles down, is an incredibly simple object. It only has three properties that you can measure from the outside.
Just three.
Just three. Its mass, its electric charge, and its angular momentum, or spin. That is it. It's a perfect, featureless sphere of geometry.
So it doesn't matter what you make it out of.
Not one bit. The recipe is irrelevant. Let's do a thought experiment. Imagine you have, say, a huge encyclopedia set. The entire knowledge of humanity, all bound in leather. You throw it into a black hole.
Okay, encyclopedia is in.
Now, you take a crate of antimatter. Very different stuff, very volatile. But it has the exact same mass as the encyclopedia. You throw that into a second, identical black hole.
Antimatter is in.
And finally, you take just a giant, boring cloud of hydrogen gas, same mass again, and throw it into a third black hole.
Gas is in. So I have three black holes made from knowledge, from antimatter, and from plain old gas.
According to classical general relativity,
Right.
Once those objects fall in and the black holes settle down, those three black holes are absolutely, perfectly identical.
You couldn't tell them apart at all.
Not from the outside. You could measure them all you want. They would look exactly the same. The black hole forgets all the detail. It remembers the total mass you added, sure,
Or, I mean,
but it shaves off all the other features.
the hair.
The hair, the texture, the material, the words written on the pages of the encyclopedia, all of that is gone from the outside view.
But, and this is a key point, in this classical view, gone isn't the same as destroyed, is it? That encyclopedia is still in there somewhere.
Correct. And that brings us to the event horizon. Classically, it's just a one-way street, a point of no return. It isn't a physical wall you can run into.
Right, it's just a boundary in space-time.
It's a boundary. If you cross it, gravity becomes so overwhelmingly strong that nothing, not even light, can get back out. So the information, the encyclopedia that crosses this line is hidden from us. It's inaccessible. But it's not erased from the universe. It's just sitting there, inside, shielded by the horizon.
It's like locking a diary in a safe and then throwing the key into a volcano.
Yeah.
You can't read the diary anymore, but the words are still on the pages, locked away in the dark.
That's a perfect analogy. And in this classical view, falling in is actually, well, pretty uneventful, at least at first.
The no-drama condition.
The no-drama condition, right. If you were an astronaut falling through the event horizon of a supermassive black hole, the gravity is so spread out, you wouldn't feel anything special at the exact moment you cross the line. You just float on through.
For a while, anyway.
For a while, yes. Eventually, you'd get torn apart by tidal forces near the center, what we call spaghettification. But at the horizon itself, smooth sailing.
Okay, so the safe is locked, the diary's inside. Classically, no problem. So why does quantum mechanics have such a huge issue with this?
Because quantum mechanics is, at its heart, a system of perfect bookkeeping. There is a core, non-negotiable principle called unitarity.
Which is basically conservation of information.
Exactly. We all know about conservation of energy, conservation of momentum, information. Quantum information is also conserved.
But I feel like I lose information all the time. I forget things. I can't remember where I put my keys.
You forget, but the universe doesn't. Think of it this way. Unitarity says that if you have the complete quantum state of the entire universe right now, every particle, its position, its spin, everything, you can theoretically run the clock forward and calculate the entire future perfectly. And more importantly, you can run the clock backward and calculate the entire past. The equations of quantum mechanics are perfectly reversible. You can play the movie of the universe in either direction.
Let's test that with an analogy. You mentioned the encyclopedia. What if I just burn it in a bonfire, watch it turn to ash and smoke? That information looks gone to me.
It's gone to you because you don't have the technology to get it back. But in a quantum sense, it is not destroyed.
Oh.
Well, when you burn a book, what do you get? You get ash, you get smoke, you get photons of light, you get heat radiating away. If you could, in theory, capture every single molecule of smoke, every speck of ash, every photon of light, and you had a ridiculously powerful quantum computer,
I could piece it all back together.
you could reverse the process and reconstruct the book. The information is just scrambled. It's encoded in the correlations between all those outgoing particles, but it's all still there. The ink is just, spread out.
So going back to the black hole, the classical picture is fine with this. The encyclopedia is just inside the safe. We can't see it, but the universe knows it's there. The movie can still be played backward. You just have to include the stuff inside the hole.
Exactly. The movie plays backward perfectly. The books are balanced. Everything is
Until
1974, Stephen Hawking publishes a paper that completely shatters this peaceful truce. He essentially said, the safe isn't just locked, the safe is leaking, and it's leaking garbage.
This is the famous Hawking radiation.
This is it. And what Hawking did was incredibly difficult at the time. He tried to mix quantum field theory, the math of particles, with the curved spacetime of a black hole. He was doing what's called semi-classical gravity, and he looked at the vacuum of space right near the event horizon.
Let's slow down here, because this is the mechanism that drives the entire paradox. The vacuum isn't really empty space, is it?
No, not in quantum mechanics. There's no such thing as truly empty space. It's a roiling, bubbling soup of activity, a quantum foam.
I've heard that term.
You have pairs of virtual particles constantly popping in and out of existence. A particle and its antiparticle. They appear, they exist for an infinitesimal moment, and then they find each other, annihilate, and vanish.
Borrowing energy from the vacuum and then paying it back. A zero-sum game.
A perfect zero-sum game. This happens everywhere, all the time, even in the space between you and me right now. But near a black hole, the rules change.
The gravity's just too intense.
It's so intense that it acts like a powerful tidal force. It can literally rip these virtual pairs apart before they have a chance to annihilate. So imagine a pair, a particle, and an antiparticle forming right on the razor's edge of the event horizon.
Okay.
One partner falls in, past the point of no return. The other partner, however, is just far enough away that it escapes out into the universe.
Then the one that escapes, it's not virtual anymore. It becomes a real particle.
It does, becomes real radiation. But here's the kicker. Energy must be conserved. That's a hard rule. You can't just create a real particle with positive energy out of thin air. Someone has to pay the energy bill.
And the black hole pays the bill.
The black hole pays. For the escaping particle to have positive energy, the particle that fell in must have carried negative energy into the black hole relative to an observer far away.
Negative energy. So it's like the black hole is eating negative calories.
That's a great way to put it. It eats a particle with negative energy, and according to Shaw, that means its mass has to go down.
So every time a particle of Hawking radiation escapes, the black hole shrinks just a tiny, tiny bit.
Precisely. This means black holes aren't eternal. They aren't the final prisons we thought they were. They evaporate. They slowly shrink over unimaginable eons. And eventually, they vanish completely in a final poof of radiation.
And this is where the paradox finally hits us. Because if the black hole vanishes, what happened to the encyclopedia we threw in?
That is the $100 billion question. That is the crisis. Because Hawking went further, he calculated the properties of this escaping radiation, and he found that it is thermal.
Thermal, meaning it's just random heat.
Random heat. Its properties, its temperature, its energy spectrum depend only on the mass, charge, and spin of the black hole.
The three hairs again. The baldness. The radiation is coming from the generic properties of the whole, not from the specific stuff inside it.
Exactly. The outgoing radiation carries no imprint, no information about the contents. It doesn't matter if you threw in an encyclopedia or a star or a crate of antimatter. The radiation looks exactly the same. So let's play the tape forward.
Okay.
You throw the encyclopedia in. The black hole slowly radiates. The radiation is pure, featureless, thermal static. Finally, the black hole disappears completely. Now you have this cloud of random radiation. Try to play the movie backward.
You can't.
You can't. There's nothing to reverse. It's like trying to reconstruct a burned book from a cloud of perfectly uniform random heat. Unlike the real bonfire where the smoke and ash held the clues, this radiation contains nothing. There's no correlation between the radiation and the book. The information is gone.
Truly gone. Unscrambled. Fundamentally erased from reality.
Erased. And that violates unitarity. It breaks the most sacred rule of quantum mechanics. It implies that probabilities don't have to add up to 100%. It means the universe is not deterministic.
So Hawking's conclusion was just too bad for quantum mechanics.
That was his bold stance, yes.
Yeah.
He famously said, God not only plays dice, but he sometimes throws them where they cannot be seen. He argued that gravity was special, and that at this level, quantum mechanics just had to give way.
I can't imagine that went over well with the particle physics community.
It was an earthquake. It started a war. And that brings us right into our second section, the active debate. Because the community did not just roll over and accept this, they fought back hard.
Okay, so the battle lines are drawn. We have a full-blown paradox. Information goes in, nothing but static comes out. The early phase of this, from 74 up to around 2012, was really defined by that famous bet, wasn't it?
It was the Black Hole War. In 1997, you had Stephen Hawking and Kip Thorne, the heavyweights of general relativity, on one side. They bet that information is lost. It falls into the singularity and it's gone forever.
And on the other side?
John Preskill, a brilliant particle physicist from Caltech, he bet that no, quantum mechanics has to hold. Unitarity is sacred. The information must be saved somehow.
It's amazing that they're placing bets on the fundamental laws of the universe. What was the prize?
An encyclopedia, of course.
Right.
Preskill specified he wanted a complete baseball encyclopedia because information can be retrieved from it with ease.
That's fantastic. So while they were placing bets, were there any actual theories about how the information could be saved? You can't just say it's saved. You need a mechanism.
Well, for a long time, the leading contender, the best idea on the table, was something called black hole complementarity.
Complementarity. Who is behind this one?
This was championed by Leonard Susskind at Stanford and Gerard Hooft. And what they tried to do was essentially have their cake and eat it too.
How does that work?
They proposed that information is effectively in two places at once, depending on who is looking. They said that for an observer standing safely outside the black hole, the encyclopedia never actually crosses the event horizon.
It doesn't fall in.
No, it gets sort of plastered onto the surface, the horizon gets scrambled up, and is eventually re-radiated back out as part of the Hawking radiation. So, for the outside observer, information is conserved, unitarity is saved.
Okay, but what about the poor astronaut who's actually falling in? They see the encyclopedia fall in with them, don't they?
Yes. For the infalling observer, nothing strange happens. They pass right through the horizon, they see the encyclopedia fall in with them, and they both head towards the singularity at the center.
Wait, hold on a second. If the information is stuck on the surface for me, the outsider, and it's falling to the center with the astronaut, that's two copies of the same information.
It is.
Isn't that forbidden? The no-cloning theorem in quantum mechanics says you absolutely cannot make a perfect copy of an unknown quantum state.
You are absolutely right, and that's where the complementarity part comes in. Susskind's brilliant, if slightly tricky, argument was that no single observer can ever confirm that both copies exist. If you stay outside, you can only see the copy on the horizon. If you decide to jump in to check the other copy, well, you've crossed the event horizon. You can never get back out to tell your friend outside, hey, I found a second copy. Since no one can ever observe the contradiction, Susskind argued, it's not a real contradiction.
That feels a little bit like a magic trick. Pay no attention to the man behind the curtain. It seems like we're twisting the rules of logic just to avoid the problem.
It did feel that way to some people, yes. But for almost 20 years, it was the best peace treaty we had between general relativity and quantum mechanics. It saved the no-drama condition so the astronaut has a smooth ride in. And it saved the information for the outside world. It let physicists sleep at night.
Until 2012.
Until 2012. That's when 4 physicists, Amhary, Marolf, Polchinski, and Sully, who are now known collectively as AMPS, published a paper that just blew complementarity completely out of the water. They introduced the firewall paradox.
I've heard this described as the menu from hell.
That's a good description. What they showed is that complementarity was fundamentally inconsistent. And their argument hinged on a very deep quantum rule called monogamy of entanglement.
Right, monogamy. This sounds more like relationship advice than physics, but let's break it down.
It's a surprisingly good analogy. In the quantum world, entanglement is this incredibly strong, intimate connection between two particles. If particle A is maximally entangled with particle B, they are a perfect quantum pair. Knowing the state of one instantly tells you the state of the other, no matter how far apart they are.
Okay, a perfect pair.
The rule of monogamy says that particle A, which is already fully entangled with particle B, cannot also be fully entangled with a third particle, particle C, at the same time.
You can't be married to two people at once in the quantum world.
Exactly, you can't cheat. So how does this apply to the black hole?
That's what I want to know.
AMPS looked at what they called an old black hole one that has been evaporating for a long time and is now more than halfway gone. At this point, for information to be conserved, the new Hawking radiation coming out must be entangled with the radiation that came out a long time ago.
Right, because if you're reconstructing the encyclopedia, the new pages have to be related to the old pages for the story to make sense.
Precisely. So let's give them names. Particle A is a new piece of radiation just leaving the black hole. Particle B is the cloud of radiation that left a long, long time ago. For unitarity to be saved, particle A must be entangled with particle B. That's marriage number 1.
Okay, A is married to B to save quantum mechanics.
But remember general relativity and the no-drama condition. For space to be smooth at the horizon, for our astronaut to not notice anything weird, that particle A must also be entangled with its partner particle that fell inside the black hole. We'll call that particle C.
Oh, I see the problem. Particle A is the cheater.
Particle A is the cheater. It needs to be fully entangled with particle B, the old radiation, to satisfy quantum mechanics. But it also needs to be fully entangled with particle C, its interior partner, to satisfy general relativity. It cannot do both. It violates the monogamy of entanglement.
So something has to give. You have to end one of the marriages.
You have to choose. And AMPS argued that, look, preserving unitarity, or preserving information, is probably the more fundamental rule. So let's save the marriage between A and B. That means you have to violently break the entanglement between A and C, the link across the event horizon.
And breaking that link has consequences.
Massive consequences. In quantum mechanics, entanglement is sort of what stitches the fabric of space-time together. If you break an entanglement link, it releases a huge amount of energy.
How huge?
They calculated that if you break these links for every single particle emerging from the hole, you create an unbelievably high-energy curtain right at the event horizon, a literal firewall.
So the no-drama idea is dead. If I'm an astronaut falling into an old black hole, I don't just float in. I hit a wall of fire, and I'm instantly incinerated.
That is the shocking implication. It completely kills the equivalence principle, which is the very foundation of general relativity. It means space doesn't continue smoothly. It says space effectively ends at the horizon in a blaze of glory.
So that's the menu from hell. Either information is lost, and Hawking was right all along, or the horizon is a wall of fire, and Einstein's theory of gravity is wrong.
And neither option is palatable. It was a genuine crisis. It felt like we had fundamentally broken physics.
Did anyone try to find a third way out? Were there any other alternatives being discussed?
Oh, absolutely. People got very creative. One of the more interesting ideas, which comes from the world of string theory, is the concept of fuzzballs.
Fuzzballs. I love these physics names. It sounds harmless, but I'm guessing the math is anything but.
It's extremely complex. The idea was proposed by Samir Malther, and he basically suggested that our entire classical picture of a black hole, this empty pit with a tiny, infinitely dense singularity in the middle, is just plain wrong.
What's his alternative?
He argued that in string theory, a black hole isn't empty space at all. It's actually a super dense, tangled ball of fundamental strings and brains, a fuzzball.
So there's no empty interior and no event horizon in the classical sense.
Exactly. The fuzzball has a physical surface, much like a neutron star, just way, way denser. And if it has a surface, the problem just evaporates.
How so?
Because it radiates from its surface just like any other hot object, like a piece of burning coal. The information is encoded on the surface, and it leaves naturally in the thermal radiation. There's no inside for the information to get trapped in. The black hole is just a really, really heavy, hot ball of yarn.
That seems to solve the paradox very neatly. But the cost is you have to throw out the entire beautiful geometric picture of a black hole from general relativity.
That's the trade-off. It solves the problem by saying black holes aren't really what we thought they were, and for many relativists, that's too high a price to pay. It destroys the elegance of the smooth event horizon.
And what about Hawking himself? Did he stick to his information is lost position through all of this?
No, actually, he famously conceded the bet. In 2004, he stood up at a conference and announced that he'd been wrong, and he handed John Kreskill the baseball encyclopedia.
Wow.
But his theoretical reasoning at the time was a bit fuzzy. It wasn't fully convincing. However, much later in his life, around 2016, he teamed up with Malcolm Perry and Andrew Strominger to propose a new idea called soft hair.
We're back to hair again, but now it's soft.
Soft, in physics jargon, means zero energy. They found that there are an infinite number of these zero-energy particles, soft gravitons and soft photons, that live at the event horizon. They argued that when you throw something into the black hole, you disturb this cloud of soft particles.
And the information gets stored there.
The idea is that the information gets stored in the configuration of this soft hair, like a kind of holographic plate on the surface of the black hole. So the black hole isn't bald after all. It has this very, very subtle peach fuzz that holds the data.
Okay, that's another interesting possibility.
It is. It showed that black holes are definitely more complex than the simple classical picture, but many physicists felt it wasn't enough. You can maybe store some information in soft hair, but can you store the entire contents of an encyclopedia? The consensus was probably not. It might be part of the solution, but it's not the whole solution.
So we've got firewalls, fuzzballs, soft hair. It just feels like a period of total chaos. Everyone is scrambling, trying to patch the leaks in a sinking ship.
It was. But that chaos set the stage for the modern era. And that brings us to the frontiers. Because in 2019, something really huge happened.
This is where things start to get really wild, but also maybe a bit more optimistic.
I would say so. This is the breakthrough that has a lot of people thinking we might actually be solving this thing for real. And it all revolves around a simple-looking graph, a plot called the Page curve.
You mentioned this before as the Holy Grail. Tell us about Don Page.
Don Page was one of Hawking's own graduate students, and way back in 1993, he decided to attack the problem not with gravity, but with pure information theory. He just asked a simple question. Assuming information is conserved, what must the entropy of the Hawking radiation look like over time?
And let's be clear about entropy here. In this context, it's basically a measure of how much information is hidden from us, right? The measure of our ignorance.
That's a perfect way to put it. So at the very beginning, the black hole is full of the encyclopedia's information, and the radiation is empty. So the entropy of the radiation is zero. We have no ignorance.
Right.
As the hole starts to evaporate, particle by particle, The radiation gets more and more mixed up and entangled with the black hole's interior. Our ignorance grows. We know less and less about the total state, so the entropy goes up and up.
That makes sense. The more the book burns, the more scrambled the information becomes.
But, and this was Page's brilliant insight, he argued that if the information is ultimately coming back out, there has to be a tipping point. That point happens when the black hole is exactly half evaporated.
The page time.
The page time. After that point, the radiation actually contains more than half of the total information. So each new particle that comes out isn't adding to your ignorance anymore. It's giving you clues that help you decode the information you already collected.
It's like having the second half of a book. It helps you understand the first half. Your ignorance starts to drop.
Your ignorance drops, the entropy starts to go down. So the curve goes up, it peaks in the middle at the page time, and then it comes all the way back down to zero when the black hole is completely gone and you have all the information back.
So that's the shape of the page curve. For decades, Hawking's calculation just showed the line going up forever.
Up and up and up. That's information loss. So the holy grail of this field became, can you derive the correct downward sloping page curve using the equations of gravity? For 25 years, nobody could do it.
Until 2019.
Until 2019. Two groups of physicists working independently, often called the East Coast team with Ahmed Almheri and the West Coast team with Jeff Pennington, they cracked it. They published papers back to back that just electrified the field. And they used a very powerful, very strange mathematical tool called the replica trick.
Replica. Okay, you have to walk me through this carefully. Is this another magic trick like complementarity?
It's a very clever and well-established mathematical tool for calculating entropy. It's weird, but it's not a cheat. The basic idea is that to calculate the entropy, looking at just one copy of the universe isn't enough. The math tells you to imagine making replicas, perfect theoretical photocopies of the entire space-time geometry.
Okay, so I'm picturing a stack of transparencies, and each transparency is an entire universe with its black hole and radiation.
That's a good picture. Now, when you perform a calculation in quantum gravity called the path integral, you have to sum up all the possible ways these universes could behave. And what they found was that you have to include new possibilities, new geometries that connect the different photocopies.
What kind of connections?
Replica wormholes, tiny space-time tunnels that bridge the gap from replica 1 to replica 2 and from replica 2 to replica 3 and so on.
Wormholes are appearing in the math itself.
Yes. Now, these aren't necessarily physical wormholes you could fly a spaceship through. They are connections in the space of all possible quantum histories. But including them has a profound effect on the answer. It fundamentally changes what we mean by inside and outside. And it leads directly to this new, crucial concept called islands.
Okay, this is the key idea. Paint the picture for me. I have the black hole, and I have the radiation flying away from it, light years away. What is an island?
So, imagine the black hole evaporating. For the first half of its life, things are as you'd expect. The inside is the inside, the outside is the outside. But after the page time, when the black hole is more than half gone, the new calculation says that the ownership of a piece of space-time suddenly shifts. A region deep inside the black hole's interior, which they call the island, suddenly, from a mathematical point of view, belongs to the radiation that's far away.
Wait. A chunk of the inside of the black hole now belongs to the outside. How is that possible?
It's possible because of these wormholes. In the language of entanglement, the entanglement wedge of the radiation suddenly expands to include this island. Think of it like an octopus.
An octopus.
I like this analogy. Imagine the head of the octopus is the island. It's a region of space sitting deep inside the black hole, but its tentacles are these replica wormholes, and they are very, very long. The tentacles stretch out through space-time and connect to the individual particles of Hawking radiation that are now light years away.
So if I'm an observer outside, and I'm collecting the radiation particles, the tentacles, I am, in a way, holding the head of the octopus, the island, which is still inside the black hole.
Precisely. Because they are all part of the same quantum system, connected by these wormholes. So any information that falls into the island is automatically, via this entanglement connection, encoded in the radiation far away. You don't need the information to physically climb out past a firewall.
It doesn't need to escape.
It doesn't need to escape because it's already out. The inside and the outside are, in this very specific way, the same thing.
That is genuinely mind-bending. The information is essentially teleported out through the geometry of space-time itself.
In a sense, yes. It's a profound shift in perspective. At a certain point in the black hole's life, a piece of its interior stops belonging to the black hole and starts belonging to the radiation cloud.
And this all relies on that other famous idea, that conjecture, ER, ER, EPR.
Yes, that's the philosophical glue that holds this all together. It was proposed by Juan Maldacena and Leonard Susskind a few years before this breakthrough. It sounds like a cryptic bumper sticker, but it's one of the deepest ideas in modern physics.
Break it down for us. ER and EPR.
ER stands for Einstein-Rosen bridges, which is the technical name for wormholes. EPR stands for Einstein-Podolsky-Rosen, which refers to quantum entanglement. The conjecture is that these two things are literally the same phenomenon.
A wormhole is entanglement.
And entanglement is a wormhole. The idea is that if you have two particles that are entangled, there is a tiny microscopic wormhole connecting them through space-time.
Even if they're on opposite sides of the galaxy.
Even then, and in the case of the old black hole, you have billions upon billions of radiation particles that are all entangled with the interior. So what you have is a vast, complex network of these tiny EPR wormholes stitching the interior island to the distant exterior radiation.
And because they are connected, space remains smooth. The firewall never forms because the wormholes themselves are the connection. They are the smooth space.
You've got it. The firewall paradox arose because we thought the old radiation, the new radiation, and the interior were three separate competing things. But if the old radiation and the interior are connected by this octopus of wormholes, the monogamy problem just dissolves. The geometry of space-time saves quantum mechanics.
So when they ran the numbers, when they did the replica trick calculation, including these wormholes and islands.
It worked. It worked perfectly. The calculation showed the entropy going up, and then right around the page time, the wormhole configurations become the dominant possibility. The island appears in the math, and boom, the entropy curve turns over and goes down. They reproduce the page curve exactly.
That must have been an incredible moment.
It was a massive triumph for the field. It really felt like after nearly 50 years, the pieces of the puzzle were finally clicking into place.
Was that it? Case closed? Paradox solved?
Mm-hmm.
Can we all stop worrying about the nature of reality now?
Laughs. Well, not so fast. This is theoretical physics. It's never that clean and simple. While the entropy calculation is a spectacular success, the physical mechanism is still, well, it's pretty fuzzy.
What do you mean?
I mean, there was a survey done very recently, the Copenhagen survey in 2024, where they polled the experts working in this field.
I love these kinds of snapshots. Physics isn't a democracy, but it tells you where the community's confidence is. So what's the verdict?
It's still very fractured. About 53% believe information is ultimately preserved, so that's a slim majority. But when you ask them about this specific island solution, only about 27% say they fully buy it as the complete answer.
Wow, that is surprisingly low for something that so beautifully reproduced the page curve.
Yeah.
What's the hesitation? Why the skepticism?
The biggest criticism is that the calculation is Euclidean. It's done using what's called imaginary time.
Imaginary time. Like the square root of -1. That doesn't sound very real.
It's not. It's a mathematical trick that physicists have used for decades. You rotate time into a fourth spatial dimension, which makes certain very hard quantum gravity calculations possible. It gives you the right answer for the entropy. It matches the page curve. But it doesn't describe the physical process unfolding in real time, in our time.
So it's like looking at the answer key in the back of the textbook.
Yeah.
You know the final answer is 42, but you still don't know the step-by-step process for how to solve the equation.
That's a perfect way to describe it. Critics argue that we still don't know the Hamiltonian, the actual physical operator, that describes how the information gets from the inside to the outside in a real evolving universe. We know the final state, but we don't know the movie that gets us there.
Are there other competing ideas still out there?
Oh, yes. There's still a significant group, about 26% in that same survey, who believe in something called remnants. This is the idea that black hole evaporation doesn't go all the way. The black hole shrinks and shrinks, and then it just stops when it gets down to a tiny stable nugget, maybe the size of a fundamental particle. And that tiny microscopic remnant contains all the information of the star that collapsed to form it.
So it's like a cosmic hard drive.
An incredibly dense one. But that idea has its own deep problems. If you can have these tiny objects with a vast amount of information storage, it leads to all sorts of paradoxes in particle physics. So the debate is far from over. The island solution is definitely the leading candidate, but it hasn't won the war just yet.
But even if the details are still being debated, the implications of these ideas, islands, wormholes, ER equals EPR, they're staggering. This brings us to our last section here, implications. What did this all mean for our understanding of reality?
I think the single biggest takeaway, the thing that keeps physicists up at night, is that space-time is probably not fundamental.
Space-time isn't real.
Hmm.
That's a heavy statement. I'm sitting in space right now. It feels pretty fundamental to me.
It feels fundamental, but it might be an emergent property, like
Yeah.
temperature. Temperature feels real, but it isn't a fundamental thing. It's just the average motion of a lot of tiny atoms.
So space-time is the same.
The idea is that space-time is built from something deeper. And if ER-EPR is true, that deeper thing is quantum entanglement. The very fabric of the universe, the geometry, the feeling of distance, is literally stitched together by these quantum connections between bits of information.
We're living inside a giant quantum computer.
A quantum quilt, maybe? And if you could somehow turn off all the entanglement, the universe would just disintegrate into a set of disconnected, random points with no sense of space or time.
It reinforces that other strange idea, the holographic principle.
It's the same family of ideas, yes.
Right.
The holographic principle suggests that all the information contained in a three-dimensional volume of space, like the room you're in, can be fully described by a theory that lives on the two-dimensional boundary of that space, like on the walls.
The 3D world is just a projection of 2D data.
A projection. And this new work is the first time we've seen the math of holography work for a realistic, evolving black hole.
This also seems to kill the old idea of locality, doesn't it? The idea that to affect something over there, I have to send a signal that travels through the space between us.
It really challenges it. The island calculation is an example of what we call large-scale non-locality. It says a region of space deep inside a black hole and a cloud of radiation particles light years away are, in a very real sense, the same physical object.
That's incredibly strange.
It means our intuitive sense of here and there might just be an illusion. The universe is far more interconnected in a non-local way than we ever perceived.
All of this seems to be building towards what some people call the central dogma of black hole physics.
It does sound a bit like a religious creed, doesn't it?
A little bit. What is it?
The central dogma is the statement that, from the point of view of an outside observer, a black hole behaves exactly like any other normal quantum mechanical system. It evolves unitarily. It has a finite number of degrees of freedom, a finite number of bits given by its surface area, and it obeys all the standard rules.
So gravity isn't a special monster that breaks quantum mechanics.
The idea is that gravity is a consequence of quantum mechanics. The 2019 results are the strongest evidence we have so far that this central dogma is correct.
But there are still deep, unresolved problems here. You mentioned we're using math that applies to scales where our theories shouldn't even work.
That's right, the Transplanckian problem. We are, frankly, pushing our theories far beyond their limits into regimes where space and time themselves should be a quantum foam. And new, subtle paradoxes are popping up, like something called state dependence.
What's that?
It's a really weird feature of the island solution. To make the math work, the very existence of the smooth interior geometry seems to depend on the precise, detailed quantum state of the radiation outside.
The inside of the house depends on the exact pattern of leaves on the trees outside.
In a way, yes. It's a type of connection between geometry and quantum states that we've never seen before, and it challenges some of the basic assumptions of quantum theory. It really feels like for every hole we patch in the boat, one or two new, smaller leaks spring up elsewhere.
But it's progress.
Oh, absolutely. It's immense progress. We have gone from Hawking's initial information is destroyed, the end, to a world where information is preserved in a holographic projection connected by space-time wormholes. That is a monumental shift in our understanding.
It certainly is, and it leaves us with some very heavy final thoughts to chew on.
It does. And maybe here's one final provocative thought for everyone listening. We've spent this entire time talking about the event horizon. We've been focused on fixing the information leak at the surface of the black hole. But these beautiful island calculations, they are strangely silent about the very center.
The singularity.
The singularity. The point where our theories say space-time curvature becomes infinite and time itself comes to an end. The island story fixes the bookkeeping for the outside observer, it fixes the entropy, but it tells us nothing new about what happens to the astronaut who actually falls all the way to the center. We may have patched the wall of the prison, but we still have no idea what the monster in the basement is.
And if the big lesson here is that space-time is just an emergent projection of entanglement,
Then you have to ask yourself, if a black hole is a kind of hologram and our universe seems to obey the same fundamental rules, are we just a holographic projection? Is our entire three-dimensional reality just the shadow of some deeper, more complex quantum reality that we can't directly perceive?
I think I need to go sit quietly for a while and just think about that.
It is a lot to take in, but
Yeah.
that's the beauty and the terror of peering behind the curtain of reality.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this exploration of the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us on Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.